We notice that there is a popular case where a long straight wire is carrying a current. Let's recall the feature of the field due to a straight wire. Please look at the figure. Due to the symmetry of the situation, the magnetic field lines are circles concentric with the wire. The plane of the circle is perpendicular to the wire. We have the same value of the field on the circles of the same radius. The field is tangent to the circle at each point. From the figure, we could also see that the magnetic field line forms a closed loop. It has no beginning and no end. This is totally different from the electric field lines. The electric field lines begin on positive charges and end on negative charges. Here we demonstrate that the straight wire carrying a current produces the magnetic field by placing some compass needles near a wire. As shown in this figure, if no current in the wire, all compass needles point in the same direction. But when the wire carries a steady current, all needles are deflected in the direction tangent to the circle. This is the direction of the magnetic field created by the current, which is consistent with the result by using the right-hand rule in above figure. When the current in the wire is reversed, the deflection of the needle is also reversed. The observations demonstrate the pattern of the field lines due to a straight wire. Now let's divide a circular path of radius r into an infinite number of small length elements. Each length element vector ds points along the direction tangent to the circle with a magnitude ds. We could evaluate the dot product of b and ds for small length element. Then integrate all products for all elements over the closed circular path. We notice the vector ds is parallel to b at each point of the circular path. So b dot ds becomes b ds. Furthermore, the magnitude of b is constant on this circle. b could be removed from the integral sign. Therefore, the sum of the products b ds over the closed path is equivalent to b times the line integral of ds, where integral of ds is equal to 2 pi r, which is the circumference of the circular path of radius r. In this case, you may notice that the path we choose is just following one particular magnetic field line. What if we choose a loop of an arbitrary shape? Please look at this figure. We choose a closed loop with an arbitrary shape. We follow the same steps to evaluate the line integral of b over the closed loop. We divide the loop into an infinite number of the length elements. The length element vector ds makes the angle theta with b at each point along the path. So b dot ds becomes b ds cosine theta. ds cosine theta equals to dr, which is the projection of ds onto the tangential line. dr equals r d phi from geometry as shown in the figure. R is cancelled and we move the constants from the integral sign. The line integral of d phi over the closed path is 2 pi. So we have the same result for an arbitrary closed loop as the one for the circular loop. This result shows us that the line integral of b around any closed loop is proportional to I, where I is the current encircled by the loop. We could also say that line integral of b around any closed path equals mu0 times I, where I is a total static current passing through any surface bounded by the closed path. This is known as Ampere's law. A closed path is also called Amperean loop. Here we have some considerations. First, how to understand the word any in the statement. For a closed loop, actually, there are infinite number of surfaces which are bounded by this loop, right? Hence, the current encircled by a closed loop must pass through any surface bounded by this closed loop. Secondly, please note, here I refers to the total current encircled by the loop. We know the current has a direction. That means this term in the equation is sign-sensitive. How we define which one is positive and which one is negative? Please apply the right-hand rule. When your forefingers curl along the direction we integrate around the loop, the thumb just points in the direction of the current. Then the current is defined to be positive, vice versa. For example, here we have I1, I2, and I3. I1 is not encircled by the loop. I2 is upward and I3 is downward. We integrate around the loop in a counterclockwise direction. Therefore, I2 is now positive and I3 is negative by applying the right-hand rule. So, we write the expression by using Ampere's law for this case. Now we think of Gauss's law in electrostatics. Ampere's law in magnetism is analogous to Gauss's law in electrostatics. In order to apply them to solve problems, the system must have a certain symmetry. For example, for a wire of an infinite length, the system has a cylindrical symmetry and Ampere's law can be applied to solve for the magnetic field. While the length of the wire is finite, the Beelzebub law must be used instead. In the next lecture, I will give you some examples to show you how to apply Ampere's law to solve for the magnetic field due to current configurations with symmetries.